We're going to do a conservation of energy problem. And it's going to be problem number 39 on page 176. And it has a trampoline artist jumping off of a platform at a speed of 5 meters per second. And he lands on a trampoline 3 meters below. And question 1 is, well, how fast is he moving when he gets to here? And then the second question asks, how far does he depress the trampoline if it behaves like a spring with a certain spring constant, which we'll discuss. So this is a typical conservation of energy problem, and I know that because there's a change in elevation. They're asking about speeds. They're telling me about speeds. So these are clues that I know this is a conservation of energy problem. The conservation of energy says work non-conservative plus potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. First thing you need to do is establish where are you going to measure all of your heights from, your elevations. So you have to choose a baseline. I'm going to choose the bottom of the trampoline to be where I call the height equals 0. So I'll measure all my heights from that point. Okay. Now, when the person is jumping off of the platform, they are obviously higher than what I'm calling the height of 0. So they have potential energy due to gravity. They're not compressing or stretching a spring, so they don't have spring potential. And they are moving at 5 meters per second. There's no air resistance to worry about this problem or friction. So I'm going to cancel out the work non-conservative. When the person gets to the surface of the trampoline, their height is now 0. So they have no gravitational potential energy. And they're not yet compressing the spring, the trampoline. So they have no spring potential. But they are moving, so they have kinetic energy. Potential energy cancels out. So I have gravitational potential energy here, mgh initial. And I have kinetic energy, 1/2 mv initial squared. That's equal to kinetic energy final, which is 1/2 mv final squared. We have an m in all of our terms, so we can cancel the m's. And we need to solve for v final. So we're going to multiply both sides of the equation by 2. Now I can solve for v final. 2 times g times h initial, which was 3 meters, plus vi squared is 5 meters per second squared. Okay, so 2 times 9.8 times 3 is 58.8, plus 5 squared is 25, gives you 83.8. Take the square root of the answer, 9.15 meters per second. So that's how fast he hits the trampoline. And we could have used kinematics to solve that, but it'd be a little more complicated. Then part B says, how far does he depress the trampoline if it behaves like a spring with a spring constant of 5.2 times 10 to the 4th newtons per meter. Okay, so here, if you think about it, the guy's going to jump off the platform, he hits the trampoline, and he compresses it a certain distance, and they want to know how far. Okay, so we're going to use conservation of energy again. And here, there's still no non-conservative forces. Okay, and I'm going to take this from when he jumps off the trampoline, or jumps off the tower, until he fully compresses the trampoline. So if you think about it, the left side of this equation is still exactly the same. He still has kinetic energy, and he still has gravitational potential because he's still elevated and he's still moving. It's the same situation. But on the right side, the way you look at it is, now he's not moving because he compresses the trampoline until he stops. So he has no kinetic energy. He does have spring potential because he's compressing the trampoline. He also has negative gravitational potential energy because now he's actually below the spot where we called the height 0. So we have two kinds of potential energy on the right. So we have mg h initial plus 1/2 m v initial squared equals gravitational potential energy at the end, which is mg times his new height, which is negative x, and I'll explain that in a second, and plus 1/2 kx squared. So where did those two terms come from? The mg times negative x is his gravitational potential energy. Since he's lower than the surface of the trampoline and he compressed it by a distance x, his gravitational potential energy is negative mgx. And the 1/2 kx squared is the spring potential energy, assuming that x is the amount that he compressed it. Okay, so I can solve this. I have mgh initial. I can plug those numbers in. 75 times 9.8 times 3 is 2205 plus half times 75 times 5 meters per second squared is 937.5 equals mg, which is 75 times 9.8, is 735 times negative x. So that's negative 735x. Okay, and then plus 1/2 k, 0.5 times 5.2 E4 is 26,000 x squared. So this is a quadratic equation that I need to simplify here. 2205 plus 937.5 is 3142.5 equals negative 735x plus 26,000 x squared. I'm going to bring the 3142 to the right side. So 0 equals 26,000 x squared minus 735x minus 3142.5. That's all equal to 0. We need to solve this for x. It's obviously quadratic, so we have to use the quadratic formula here to get the solution. There's going to be two solutions, one of which is nonsense because x will be negative, and the other one will be x positive, which is the one we're looking for. So when we do that, plug in our numbers, and solve it, we get 0.35 meters for x, which is how much he compresses the trampoline.